The quicksort is another example of divide and conquer algorithm. And yeah, based on the name, first it's sorting algorithm, obviously. Second, it must be quick, right? Otherwise it wouldn't be called quicksort, right? Yeah. So let's have a look. So this algorithm was proposed by this guy, okay, C.R. Hoare, in 1962, okay, about a little bit more than like a half a century ago, okay. But this is a famous divide and conquer sorting algorithm. Like, I mean, so far the sorting algorithm that falls into like divide and conquer, obviously the merge sort, right, is one of the examples. But the quicksort is an even more interesting one. Okay. In the quicksort, we are able to sort in place. Okay, kind of like insertion sort, but not like merge sort. So what is in place? In place means like you don't need additional. No, because you want to sort n numbers, right? I mean, sometimes you need like some additional space to help you sort the numbers, right? Yeah, if you only need like some constant number of space to help you to do the sorting, I mean the majority of the time you keep these numbers in the original storage space, in the original array. We call that in place. Okay, for example, in the insertion sort, you know, I mean, you need to do sometimes you need to do some swap, but most of the time you keep all these numbers in the array, right? So that's what we call in place. But the merge sort is not, because merge sort, remember, for two sorted lists, you need to combine them into one, like a sorted list. I mean, in this combination process, obviously you need one additional space of size n to hold these two sublists together, right? So that is why the merge sort is not an in-place sorting algorithm. Okay? Because you need, you know, the additional space of size, you know, n in order to do the sorting. Okay? So, okay, and it's very practical. I mean, with tuning, like actually, like with not, you don't need a lot of tuning. It's already quick enough. But I have to tell you that there are more than one implementation of quicksort. Okay, the one introduced in the book, okay, in the textbook, is not the one that I learned when I was a student. Okay, but the basic idea, I mean, is similar. The basic idea is similar. Okay, I will explain like both idea to you later. I mean, actually, like this idea, the other idea, I mean, you can also find it in the textbook. Okay. But anyway, okay, I'm not sure if I have enough time today. I should have enough time today, at least to talk about the idea. So what is the quicksort? Remember the merge sort. The merge sort, the divide is quick, right? It doesn't take much effort to do a division, right? The conquer, as I said earlier, I mean, most of the time the conquer is done by recursive call, right? So not much programming. And in the merge sort, the difficult or the complicated part happens in the merge part, which is like a combination, right? Okay. So in the quicksort, the idea is exactly opposite. The difficult part or the complicated part happens in the divide. the conquer is always like just recursive call. Okay. And the combine is trivial. The combine is trivial. Okay. So what is the divide? The divide is like this. First you find a number. You find a number. This number, usually we just get the first number in the array. Usually. I mean the easiest approach. But it doesn't have to. It doesn't have to. Okay? But anyway, once you get this number, we call this number x. Okay, I mean in here, in this figure. But in algorithm, in the quicksort algorithm, there's a special name for this number. We call this number pivot. Okay, so when I say pivot in the quicksort, you should be able to understand what I meant. Okay, so this pivot, okay, in the divide, okay, at the end of this divide process, at the end of the divide process, the important thing is you have to put this x here such that all the elements in front of it are they are smaller or equal to x. And all the elements now behind it, they are greater or equal to x. Okay? So that's the basic concept of this divide. Okay, at the end of this divide process, you want to achieve that. And, I mean, it doesn't mean this part and this part, they are sorted. No, they are not necessarily sorted. It just means like the elements here are smaller or equal to x. The element here, they are greater or equal to x. Okay, that's only requirement. And also, it doesn't mean the size here and the size here, they are the same. No, they are not necessarily the same. A lot of time, actually most of the time, they are different. Okay, it doesn't matter. It doesn't matter. Okay, I mean in the worst scenario, one of them could be empty set. Okay, if you happen to pick your pivot to be the minimum element or the maximum element, then one of these areas should be empty. Okay. But one thing for sure is that at the end of the divide, the pivot is already in the rightful place. It doesn't have to be moved any longer. It is already at its final location. Right? Right? Think about that. Is that right?
Yes.
Okay. So that's the basic idea of quicksort. So the key idea is that how do we make sure this divide take only linear time? Okay, so here's the algorithm. But before I talk about this algorithm, I would use an example. Okay. But before I talk about the example, I will first have to talk about this invariant. So this invariant, what is this invariant? First, x is what I meant, pivot, right? Okay. During the process, this x is the pivot. At the end, x will move to the rightful place. Okay? So now, okay, this purple part is the area that we are already sure they are greater than, they are smaller than x, smaller or equal to x. Okay, and this orange part contains the elements that we are sure they are greater or equal to x. Okay, and the green part is the part we do not know yet. We haven't processed it. Okay, so you could imagine initially before you start doing any process, they will be empty. The green part and the orange part will be empty, right? And except the x, the pivot itself, all the other part belong to green, right? Because we haven't processed anything yet, right? Okay. So, I will come back to this algorithm, okay, later on, but the idea, let's look at this. So as I said, initially, okay, this is our pivot, the first element. And all the other elements, we haven't processed them. So they are, colored green, right? By the way, let me give you one more information. The I indicate the index of the last element in the purple part. Okay, so because initially we don't have anything for I, right? For the green, for the purple part. So I actually will be sitting at the same place as at X. Okay, and the J, what is J? J is in the beginning of the the green part, that the elements that haven't been processed. So you can see, J is here initially. I is here. Okay, and there's no green part. There's no there's no purple part. There's no orange part, right? So far so good, right? Okay, so now let's start doing the job. So how do we do the job? We start checking the first element and see if it is greater or equal or smaller than your pivot. Okay? If it is if it's greater than the pivot, you will grow the purple part. If it is smaller than pivot, you'll grow the purple part. Right? That's the basic idea. Okay? So you check 10, right? 10 is greater than 6. So we will grow the purple part. So the J gets advanced to here, but I stays here. Right? And then the next element we check. We have 13. Okay, 13, yeah, because J stands for the first element that has not been processed. So we process the place that the J is pointing to. So 13 is greater than 6. So again, we advance J to the next one. Nothing need to be done. So this is still marked as like orange. Well, is it orange or pink? I'm not sure it's orange or pink. Is it? I'm not sure. Oh, sorry. This I should have called this pink. But anyway, you get an idea. I may refer to wrong color. Maybe I'm colorblind. Okay, but you get an idea. Okay, okay. So anyway, so now we are here, and then it's 5, right? Now we look at 5. 5 is smaller than 6, right? So what do? We need to keep 5 in. We need to move 5 in front of the pink part, right? So what happens is that we just do a swap between 5 and the first element in the pink. Okay. So what happens is like we do a swap. And then we advance the index I, no, I mean here. The I, as I said, it points to the last element of the purple part. Okay? So we continue advance, we continue like, I mean, J gets advanced to the next one. Yeah. And we try to compare 8 with 6. 8 is greater than 6, so nothing needs to be done. And again, 3. 3 is smaller than 6. So we need to swap 3 with the first element of the pink part. So 3 and 13 get swapped. And I gets advanced by 1. J gets advanced by 1. Okay, after the swap. So we swap, I advance to here. And the J need to advance to the next one. And 2 is again smaller than 6. Again, we need to swap 2 with 10. Okay, so, you know, and then advance I and J. So what happens is that it becomes like this, and then, you know, I advance, J advance to here. And 11, the last element, 11 is greater than 6, so nothing needs to be done. So, at this moment, it is stuck, right? When it is stuck, we need to move 6 at the rightful place, right? Where do we move it? We move 6, we try to swap 6 with the index I. Okay, so that's the result. And as you can see, the elements here are smaller than 6. The element behind 6 are bigger than 6. They are not necessarily sorted, but the 6 is already in the right place. Right? And I mean, you can check the algorithm. The algorithm basically is doing exactly what I was talking about. So you see, okay, X, I mean, it's a pivot. We store this pivot here, and I start from the first element, you know, and then J start from the second element, because like initially, it's like this, right? Okay, and then, you know, for J element that's pointed by J, that's the first element that's not processed. We compare with the pivot X. Okay, if it's greater than, if it's smaller than the pivot, we need to do a swap. Okay, I mean, otherwise, like we just advance. Then, I mean, we need to, you know, make sure like the index get taken care of, and then that's it. So, but here, okay, what is time complexity for this? Because each comparison, we finish one element. That element is already taken care of. We already mark that element either into pink or into purple, right? So basically, like, so the green, the element that's not processed, the green elements, you know, after each comparison, the purple, the green element gets reduced by 1, right? And after each comparison, we only need to do a constant time of operations, right? So that is why, you know, the complexity, okay, the only additional operation is at the end, we need to do a swap to put pivot in the rightful place. That's, again, a constant time operation. So that is why this partition is taking constant time. Sorry, taking linear time. It's taking linear time. Okay? So, so your the pseudocode for pixel is very, very simple. A, P, R. P and R stands for the range of the array that needs to be sorted. Okay, the P is the first element. Okay, it indicates the index of the first element. R indicates the index of the last element. Of course, if P is smaller than R, then we are going to do the partition. Okay, we try to, this partition basically, at the end, okay, this Q is where the pivot is located. You will return the location of the pivot. Okay, and that place, as I said, it's already sorted, right? It's already in the rightful place. So we need to only take care of starting from P to Q minus 1, the previous element. We call the quicksort again, recursively, to deal with the previous elements. And for the elements behind the pivot, okay, Q plus 1 to R, we call the quicksort recursively. So these are two recursive calls. This has to be two recursive calls. They are different, okay? And we need to have an initial call, quicksort A1, and to pass this the P and R into the quicksort algorithm. Okay, so this is very, very elegant. But of course, the part that is, the partition is here. The partition procedure is here. It takes a constant, linear time. It takes linear time. So, yeah, maybe let me spend maybe 10 minutes, less than 10 minutes to talk about the other idea, how the quicksort gets implemented, it is also mentioned in the textbook, and it is used in other textbook. Okay, I mean basically any of them is considered quicksort because I mean the higher level the basic idea of quicksort, as I said, is to achieve this one at the end, right? At the end of partition. So the idea of let me start from this example. Let me just try to run this, that one by this example, and then we'll continue our discussion. 6, 10, 13, 5, 8. 13, 5, 8, 3, 2, okay. So just like this one, we assume the first element is pivot. Okay? So this is the pivot. And then this is I, this is J. I mean the other quicksort. Okay. I mean the IJ are slightly different. But the idea, okay, is also very simple and very effective. I mean, it is also linear time. Okay? So the idea is like this. Okay. We we start from the right side. I mean, we basically just try to compare the elements with 6. Okay, so if this is 11, right? We start from here. 11 is greater than 6, so we move to here. 2. Okay, so we keep the left side is moving to the right. The right side moving to the left. Okay, the left side stops when it encounters an element that is greater than 6. So with this one, we stop here because 10 is greater than 6. If 10 is not greater than 6, we keep moving. Okay? And here we will move left, continue moving left, and here we see something, an element that is smaller than 6. If it is not smaller than 6, we keep moving. Okay? So when both sides stop, you can see this is 10. This is 2, right? Both are not right? We don't want the big element at the beginning. We don't want the small element at the end, right? So we do a swap. Instead of so here we do a swap. So it becomes like, so it's still 6. And this 10 becomes 2. And 13. 5. 8. 3. And this 2 becomes 10. And 11. Right? 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 And then, okay, after the swap, okay, this index I move to the right until it finds something that is element that is greater than 6. So 13 is greater than 6, we stop here, right? And we move to here, this one is already greater than 6. So we move to the left until we find something that is smaller than 6. So 3 is smaller than 6. So this is J. Again, we need to swap I and J. This is I. So after the swap, 6, 2. So it becomes 3. And 5, 8. And this 3 becomes 13, 10, 11, right? Right? We do a swap between 13 and the 3. So 3 move to here, 13 move to here, right? So now we move I again, to the right until we find something that is greater than 6, right? So it's here, right? Okay, 8 is greater than 6, so I is here. And the J, okay, again, we move to the left until we find an element that is smaller than 6, right? So this is J, right? When they go across each other, we stop. We stop. And then, we move. We swap 6 with 5. Okay, the last element that is smaller than 6. Okay, so it becomes 5, 2, 3, 6. So 6 is in the rightful place. 8, 13, 10, 11. Okay, so this idea, every comparison, we still advance at least, we still get rid of at least 1 or even 2 elements, right? So it is still linear time. Okay, it is still linear time. Yeah, it achieves like the partition. Just like this partition algorithm. Basically, but it's like we are moving from both 2 ends. We are moving from 2 ends.